It came from beyond our solar system, a mysterious wanderer streaking through the cosmic dark. It went behind the sun, but now it has reappeared. The interstellar visitor has returned, but it's strangely glowing brighter.
What if a cosmic visitor shattered every expectation? Within an hour, an unnoticed object beyond our solar system erupted in brightness, a fourfold surge that left astronomers reeling. Telescopes pivoted, orbiters burned fuel, and the world's top scientists scrambled for answers. The source, 3I Atlas, has defied all known behavior of interstellar objects, sparking debates and late-night meetings across the globe. Whatever it is, its strange rapid flare has upended astronomy's certainties, and time to understand it is running out. The sudden brightness surge. In the early hours, an amateur astronomer in Germany named Maria Schulz was closely monitoring 3I Atlas with her 12-inch telescope when something unexpected happened. At precisely 1:14 Coordinated Universal Time, her photometry software flagged a rapid increase in brightness, a staggering 1.4 magnitude jump in just 6 minutes. This means the object became about 4 times brighter almost instantaneously, a phenomenon rarely seen in comets or asteroids, which typically brighten more gradually. Intrigued and cautious, Schultz double-checked her calibration stars and redid her analysis, but the spike held firm in the data. What makes this brightness jump more puzzling is its shape on the light curve, a clean vertical leap with no signs of gradual build-up or decline. Normally, changes in brightness follow a distinct pattern tied to the object's rotation, exposing fresh ice or dust to sunlight in a cyclical way. But here, there was no periodicity, no repetition, only an abrupt, step-like surge that settled at a new, higher brightness level with no return to the previous state. This kind of behavior defies established models of comet or asteroid activity. To rule out any possible error, Schultz shared her raw light curve on a global amateur astronomy forum, seeking confirmation from others. Within just 30 minutes, observers from New Zealand and Arizona independently uploaded data showing the exact same rapid, non-repeating brightness jump. Multiple telescopes, using different equipment in vastly different locations, were capturing the same unexplained event. This collective confirmation not only reduced the likelihood of instrumental glitches, but also set the stage for a much larger mystery. The speed and clarity of the surge stood out starkly compared to previous events. For example, the famous Comet Holmes outburst in 2007 recorded a 14-magnitude increase, vastly larger but stretched over nearly 2 days. Even Oumuamua, the first recognized interstellar visitor, never exhibited such a sudden brightness change. Considering these comparisons, the sudden fourfold brightness jump in just 6 minutes is unprecedented, shaking the foundations of what astronomers expect from natural objects traveling through our solar system. Skepticism is a natural part of astronomy, especially with unusual findings. Small telescopes can be misled by clouds passing, tracking errors, or camera glitches. But Schultz's data was sound. Multiple exposures, clear skies, consistent comparison stars, and no sign of atmospheric interference. When other amateurs reported identical results using entirely different instruments, the chance of a shared mistake or coincidence dropped dramatically. This reinforced the notion that something genuinely unexpected was happening to 3I Atlas. Professional astronomers and large survey telescopes, including the Atlas and Pan stars systems, were quickly alerted to the anomaly. Their automated archival data showed matching brightness jumps, time-stamped down to the minute, confirming the amateurs' reports with high precision. This cross-validation between citizen scientists and professional observatories gave the anomaly undisputed credibility. It also added weight to the puzzle. No known natural process explains this kind of instantaneous, sustained brightness increase. Common explanations, like outgassing, where a comet suddenly releases jets of vapor and dust, cannot account for the clean, vertical leap observed. Similarly, fragmentation events that produce clouds of debris tend to show a gradual ramp-up rather than an immediate step. None of the established phenomena, whether rotational spin changes, ice fractures, or other outbursts, match this sudden behavior. The data simply doesn't fit any familiar pattern, leaving astronomers with more questions than answers. The mysterious surge became the first in a series of anomalies, each more perplexing than the last. It was the spark that ignited a frenzy of observations and analyses worldwide. But beyond the data itself, the nature of the global reaction to this event would soon reveal just how important this mystery had become. Even as the brightness anomaly grabbed attention, the story was just beginning to unfold in communities far beyond Maria Schultz's backyard. Confirmations across the globe. Within minutes of the initial report, the world's amateur astronomers galvanized into action, transforming routine observing nights into a coordinated global campaign. Digital forums and citizen science platforms buzzed with alerts as hundreds refreshed their dashboards to track 3i Atlas. Light curves from Oakland matched Schultz's spike to within seconds, while live photometry streams in Tucson detected the brightness leap in real time, sparking excitement and disbelief among both observers and online viewers. The rapid spread of data was breathtaking. Screenshots and raw measurements flooded Discord servers and Telegram groups, each new upload adding another piece to the puzzle. By 200 hours Coordinated Universal Time, the largest citizen science aggregator, Skywatch Collective, issued a flashing alert on its homepage, confirming the non-periodic brightness jump had been observed on 4 continents. Their distributed dashboard lit up with green checkmarks as observers submitted unfiltered plots and raw files, creating an open channel of transparency not often seen in astronomical discoveries. The public response was intense as well. Traffic to Skywatch's site surged tenfold, peaking at over 120,000 simultaneous viewers, shattering records previously held during major meteor storms. Hashtags like #3i Atlas anomaly and #interstellar spike trended across social platforms, drawing not only amateur astronomers but also journalists and data enthusiasts who sensed a potentially groundbreaking event in motion. Live streams shifted focus, abandoning casual sky tours for tight coverage of 3i/ATLAS, with some broadcasters staying online for hours as new data rolled in. Professional validation kept pouring in, deepening the intrigue. A Hungarian observer synchronized videos overlaying Schultz's data with his own, showing the spikes aligned with almost eerie precision. A team of undergraduates in Sao Paulo posted pre-processed datasets, complete with calibration notes, inviting community scrutiny. This crowdsourced collaboration meant errors were rapidly flagged and corrected, but none undermined the anomaly's authenticity. By sunrise across Europe, observatories ranging from backyards to university facilities reported identical sudden jumps in brightness. The magnitude and geographic spread of these confirmations left little room for doubt. Terabytes of raw photometry data were archived within 12 hours by distributed science platforms that generated thousands of reposts, driving the anomaly into multilingual trending topics. This was no isolated glitch. It was a globally echoed signal, amplified through the vast network of observers united by curiosity and urgency, each confirmation reinforcing the narrative that something unprecedented was taking place. Such a vast relay of data is rare in astronomy. Typically, observations trickle in slowly, scattering across days or weeks. Here, every node in the worldwide network seemed to pulse in sync, amplifying the urgency to understand what could cause such a sudden and sustained jump in brightness. The grassroots effort built momentum rapidly, setting the stage for professional institutions to take up the challenge. This collective responsiveness transformed what began as a peculiar amateur report into a serious scientific alert, forcing major observatories and space agencies to reconsider their priorities and resources. When professional astronomers joined the conversation, the scale of the response was about to grow exponentially. Professional and institutional response. At the Jet Propulsion Laboratory's Deep Space Operations Center, the usual overnight monitoring routine was abruptly shattered by an urgent alert. The Deep Space Network antennas in California, Madrid, and Canberra, which normally rotate through scheduled tasks supporting Mars rovers, Voyager, and other planetary missions, were suddenly faced with a top priority request. Radar tracking for 3I Atlas was demanded immediately, justified by the unexplainable brightness anomaly confirmed across multiple independent observers. The stakes were high. Redirecting antenna time meant cancelling over 22 hours of telemetry from Mars surface missions, including Perseverance and Curiosity. This telemetry backlog risked overflowing onboard memory, potentially causing data loss. The last time such an override occurred was during a potential asteroid impact event, underscoring the severity of the decision. Mission leads from various teams debated intensely, weighing the loss of invaluable Mars science against the pressing need to capture radar data on the enigmatic interstellar visitor. 17 minutes after the emergency meeting began, the vote was unanimous. The Deep Space Network's 70-meter dishes were reprogrammed live to pivot away from Mars and lock onto 3I Atlas. The decision was logged and broadcast to all affected projects, signaling a firm institutional commitment to prioritizing this single object over scheduled science. For the next day, the world's most important deep space antennas focused on an object that defied explanation, trading routine observation for a chance at breakthrough discovery. Meanwhile, the Mars Orbiter operations team faced a critical choice. Extending the orbiter's observational window by 2 hours meant executing a delta velocity maneuver, firing thrusters for 2 minutes and burning over 5 kilograms of hydrazine fuel. This may seem small, but for aging spacecraft with strictly budgeted propellant, it meant sacrificing a significant fraction of the orbiter's remaining life. The decision was irreversible, a one-way door cutting into mission longevity for the sake of capturing rare data. Engineers ran careful simulations to confirm the orbiter could still be safely decommissioned at mission's end. The science team argued passionately that no other assets could replicate the unique observation geometry from Mars' orbit, and this non-repeating event might never happen again. Ultimately, the program manager signed off on the maneuver, and thrusters fired as scheduled. In the mission logs, this fuel expenditure was flagged in red, a testament to the high stakes placed on understanding 3I Atlas. Observing priorities shifted globally as well. At the European Southern Observatory's Very Large Telescope, months of planned exoplanet transit monitoring were wiped out when commands came through to pivot all instruments to 3I Atlas. Gemini North in Hawaii received a similar directive, overriding principal investigator protests. China's Fast Radio Telescope abandoned its pulsar timing campaign, turning toward the interstellar visitor's coordinates. Each observatory's allocation committee scrambled into emergency sessions, reckoning with the costs, hundreds of hours of lost science, delayed grants, and disrupted international collaborations. The override protocol, rarely invoked and reserved for crisis moments like Shoemaker-Levy 9 or Oumuamua, was activated once again. But this time, the justification went beyond planetary defense. It was a recognition that something fundamentally new could be unfolding. This global unity framed a historic scientific moment where competition gave way to collaboration. The International Astronomical Union's Executive Committee convened in an emergency encrypted session. 11 voting members, representing continents of scientific infrastructure, debated the motion to prioritize, coordinate, and mandate data sharing on 3I Atlas. With an 8-2 vote, the mandate passed. Member observatories were ordered to withhold public statements until verification but share real-time data, underscoring the seriousness and caution enveloping the event. The union's authority threw the full weight of the global community behind the effort. The rare combination of amateur vigilance, professional urgency, and coordinated institutional action painted a picture of an event not to be ignored. Yet, despite this unprecedented focus and the resources pouring in, the best explanations remained just out of reach, hinting at a deeper mystery still waiting to be uncovered. The brightness surge had revealed something startling, and the rapid confirmations fanned the flames of urgency, but the professional and institutional response marked the moment when the cosmic anomaly could no longer be sidelined or dismissed. Technical and scientific challenges. Despite the overwhelming confirmation of the brightness surge, scientists quickly grappled with 3i Atlas behaved so anomalously. Traditional mechanisms that cause changes in brightness, such as outgassing, fragmentation, or rotational variations, don't explain the sudden vertical jump in luminosity. Outgassing produces jets of gas and dust, but its effect typically unfolds more gradually and irregularly, often accompanied by observable debris or changes in spectral signatures. Fragmentation generates clouds of fragments that brighten steadily, not in an instantaneous leap, and rotation-driven brightness changes produce rhythmic, periodic curves that were entirely absent here. The clean, step-like nature of the brightness spike defied known comet and asteroid models, leaving researchers with few natural explanations. Even the most comparable event, the famed Comet Holmes outburst in 2007, evolved over 2 days rather than minutes, and its cause, a rare shell fracture of the nucleus, does not match the swift, stable rise observed 3i Atlas. The anomaly's persistence after the spike, with no decay back to baseline, deepened the puzzle. If this was not due to surface activity or breakup, what else could cause such a sudden increase in reflected or emitted light? Rigorous skepticism was the norm, especially since early photometric observations can be prone to environmental or instrumental errors. Clouds, minor tracking misalignments, or camera glitches can produce false spikes, but multiple exposures under different atmospheric conditions all showed the same result. Confirmations came from distinct telescopes on different continents equipped with varying technologies and wavelength sensitivities. The consistency was undeniable. Those who initially doubted quickly conceded that this brightness leap was real and significant. To ensure the anomaly was not an artifact, numerous teams meticulously examined calibration procedures and cross-checked star fields for variability. The amateur group's open data sharing accelerated this verification process, enabling unbiased peer review and artifact rejection. Large professional surveys, whose automated archives offered minute-to-minute logs, also confirmed the timing and magnitude of the jump. Such widespread, independent confirmation is rare and speaks volumes about the anomaly's authenticity. The inability to attribute the brightness surge to familiar physical causes challenged long-standing assumptions about interstellar objects. It raised questions about the object's composition, surface properties, and internal structure. Perhaps it was something with a unique makeup or an unknown mechanism triggered by conditions outside our solar system. Alternatively, it might represent a new class of transient astronomical phenomena yet to be understood. Researchers also debated the possibility of non-natural explanations, but tread carefully due to scientific rigor and lack of direct evidence. Any hypothesis needed to withstand stringent scrutiny amid extraordinary claims, so natural causes remained the focus even if elusive. The data forced astronomers to reconsider models or develop novel theories that might better account for such sudden luminosity jumps. While questions swirled, the broader picture grew ever more complex as new and independent anomalies began coming to light, further complicating the attempt to interpret this unprecedented event. The mystery deepened as astronomers uncovered puzzling phenomena beyond the brightness spike alone. Emerging anomalies beyond brightness. As data collection intensified, 3i Atlas, revealed anomalies that stretched far beyond its dramatic brightening. Radar teams at Goldstone and Canberra began tracking its motion with precision, searching for subtle accelerations hinting at non-gravitational forces. Within just a few observation cycles, they detected a persistent acceleration nearly 4 times stronger than solar radiation or standard outgassing could explain, evidence of something driving the object beyond known physics. Infrared readings from the James Webb Space Telescope deepened the mystery. Its spectrometer recorded a stable thermal plateau about 30 Kelvin warmer than expected for its solar distance. Teams repeatedly verified the data, ruling out calibration or background errors. The sustained warmth implied an internal heat source or exotic process, unlike anything seen in conventional cometary activity. Then came the most startling clue: faint gamma-ray bursts captured by the Fermi and Swift observatories, precisely aligned with 3I Atlas coordinates. Such high-energy emissions have never been observed from a comet, asteroid, or any small solar system body, suggesting powerful, unknown mechanisms at play. Individually, these findings might have been dismissed as noise or coincidence, but together, the unexplained acceleration, excess heat, and gamma activity formed a coherent pattern demanding serious attention. The data painted a picture of a highly unusual interstellar object that doesn't fit any existing classification, hinting at new physics or materials beyond current understanding. Global observatories scrambled to maintain coverage, coordinating in near real time despite limited telescope access and competing priorities. Much of the analysis now proceeds quietly behind institutional doors, awaiting verification before public release. For scientists and observers alike, 3I Atlas stands as a living enigma, an object whose behavior challenges the boundaries of known astrophysics and invites us to rethink what's possible among the stars. As the pieces mounted, the silence and caution from the scientific community grew more palpable, reflecting the gravity of an unanswered and expanding cosmic mystery. The shockwave from the brightness anomaly had evolved into a symphony of unexplained signals, each demanding scrutiny and hinting at deeper truths still waiting to be revealed. The unanswered mystery and its implications, despite global scrutiny, 3I Atlas remains a profound enigma. Its sudden sustained brightening, odd trajectory shifts, unexplained warmth, and faint gamma emissions form an unprecedented pattern in interstellar observation. These anomalies have forced astronomers to suspend routine work and re-examine their assumptions about objects from beyond our solar system. Following an emergency session by the International Astronomical Union, communication grew unusually quiet. Researchers have withheld public speculation, suggesting that ongoing analyses may challenge core astrophysical models. The reallocation of telescope time and spacecraft fuel underscores the gravity of this event. Resources diverted only when something truly extraordinary is at stake. Radar data reveal a persistent acceleration not explained by known forces, while elevated heat and gamma signatures hint at exotic processes or materials. Together, these clues suggest that 3I Atlas may represent a new category of interstellar object, or even physics yet to be understood. The silence surrounding it is striking. Historically, open excitement has followed major discoveries, but now caution prevails. Scientists may be grappling with implications that stretch the boundaries of established theory. Behind closed doors, global teams continue modeling and cross-checking vast datasets, aware that premature conclusions could mislead. 3I Atlas stands as a mystery on the brink of revelation. Whether it heralds new physics or an unrecognized natural process, it has unified the scientific world in both awe and restraint, a reminder that the cosmos still holds surprises capable of rewriting our understanding. We've seen how a sudden and inexplicable brightness surge sparked a global scramble of observations, institutional overrides, and unprecedented cooperation. This mysterious object, 3I Atlas, continues to challenge experts with anomalies that defy current understanding. If you found this journey fascinating, make sure to like and subscribe for more deep dives into cosmic mysteries and the frontiers of astronomy.